Hello everyone, welcome, thank you for being here. So in this talk we're going to be considering multi-agent learning, but on games which have a network structure. Of course that's a very vast field and there's a lot of things to unpack in that, so what we'll do is we'll narrow our attention on learning via fictitious play and on a specific network game model given by the network aggregative game. So of course we're going to begin by defining each of these concepts and then we'll look at what happens when we bring them together? What kind of results can we expect from the application of fictitious play on network aggregative games? Of course, the details for these arguments and these results can be found in the accompanying paper. So we'll keep things a little bit more holistic in this talk and more towards a view for the experiments and the open questions in this area. So to understand fictitious play, we begin with the notion of the best response in game theory, which can be described through the following example. Let's say we have the rock, paper, scissors game played by two agents, A and B, and A plays the strategy rock. Then the best response of B is the strategy which maximizes its payoff given the behavior of the other agent. So in this case, we have that the strategy of the agent at some time k is rock. So agent B will look through its strategy and find the strategy which maximizes its payoff, which in this case, of course, is paper. So the best response to rock is paper. And of course, we can define this the other way. Now, this leads naturally to the notion of the best response algorithm or the best response dynamic, in which each agent updates by playing the best response to the opponent's current strategy. And this has the advantage that the fixed points of this algorithm, should they be reached, are exactly the Nash equilibria of the game. But there's a problem to this algorithm, in that it requires that the agents update according to the current strategy of the opponent, which of course doesn't take into account the history of play. So to deal with this myopia, fictitious play requires that the agents keep track of the time of the entire history of play and compute a running time average, which we denote. If we call this the strategies played by agent A and this the strategies played by agent B, we take the time average of all the strategies seen so far and we call them alpha x at some time k and alpha y at some time k for agent 2. Now, fictitious play requires that we play the best response again, but this time, instead of playing them to the agent's current strategy, we play them to the time average of the strategies seen so far. Now, this shares the exact same property that the fixed points are the Nash equilibria of the game, but it allows for the history of play to be taken into account when implemented. So much for fictitious play. What about network aggregative games? Well, in this model, we have a set of agents, and let's pick some agent and call them K. Now, in a two-person game, K would only have one opponent. In a general population game, agent K might be interacting or engaged in a multiplayer game with the entire population. However, in a network aggregative model, the agents will only see their neighbors. So in this case, K has two neighbors, the blue agent and the red agent. But as a note, we also include in our analysis the case in which K is actually connected to itself so that it can account for its own strategy when updating. But once it has the strategies of its neighbors, the network aggregative model requires that agent K should take a weighted average of the strategies played by these agents, and in doing so, compute a reference vector. So this reference vector, sigma K, is simply the weighted average of all of the strategies of K's neighbors. This reference vector then becomes the opponent which agent K sees and plays against. So we've taken a population game or a network game and decomposed it down into a series of two-person games where each agent is only engaged in an interaction with their reference vector. It's on this model and against this reference vector that the agent uses the fictitious play strategy. So they'll keep a running tally of all of the reference vectors that they've seen throughout the history of play and respond to the time average of those by playing the best response. So what kind of results can we expect of this? Well, we start with the case of zero-sum games in which agents are engaged in a purely competitive environment. And one of our first results is that the fictitious play algorithm allows the agents to converge to a fixed point. And more specifically, in the case where there aren't any of these self-loops that we mentioned earlier, then the fixed point that is reached is exactly the Nash equilibrium of the game. Now, whilst this is an important result, we know that not all games are zero-sum. And so once we apply the fictitious play algorithm on a zero-sum game, we can expect convergence, as we see on the left. But outside of this class of games, we can see that in this particular example, which isn't a zero-sum game, that fictitious play doesn't converge to an equilibrium. Rather, it seems to be converging to a limit cycle. So we can see from this that we can't take the convergence property for granted outside of this class of zero-sum games. So to alleviate this, we decide not to look at convergence to an equilibrium, but rather look at the no-regret property. Now, the idea of regret in an algorithm is that no single action that the agent could take could outperform the learning behavior. So in this particular example, the algorithm has learned a sequence of choices as to whether to take an umbrella or whether to take sunscreen, depending on the weather. Now, as you can see, just taking if we would take the umbrella every single day, or if we would take the sunscreen every single day, we wouldn't outperform the strategy that's been generated by the learning algorithm already. This is the idea of no regret. And its importance comes in the next result, which is that in the network aggregative game, in any network aggregative game, this time not just zero-sum, but in any game, regardless of the payoff structure, fictitious play will achieve this property of no regret, i.e. no singular action will be better off than playing fictitious play for any agent. Now, having established these two results in convergence, we start to look a little bit more towards an experimental analysis of fictitious play. So the first thing that we look at is we revisit this strategy in which there was no equilibrium reached. And we ask, okay, what if at each time step, a small amount of noise is added to the reference vector so that the agents are playing against a noisy signal? And what we find is that when a small amount of noise is added, very small amount, as you can see on the left here, the cyclic property or the non-convergent property still remains. But in fact, as noise is added, the dynamics start to converge, and they converge directly to the Nash equilibrium. So instead of complicating matters, adding noise seems to simplify the dynamics. And in fact, if we take a system in which convergence is guaranteed, so on the left here we see a zero-sum game with fictitious play applied on it, and we know that it will converge. But if we add a little bit of noise, what we see is that the system still converges, but to a different equilibrium. And the more noise we add, the further the equilibrium departs from the Nash equilibrium, or the original Nash equilibrium, which existed when there was no noise. And we can see that this property holds in general because if we continue to add noise, then the equilibrium shifts, but it doesn't shift away from the Nash equilibrium forever. In fact, on the leftmost graph, we see that we see on the x-axis an increase in the variance of the white noise added to this reference signal. And on the y-axis, we see the distance of the new equilibrium from the original Nash equilibrium. And we can see that whilst we initially depart from the Nash equilibrium, this behavior eventually asymptotes. It doesn't continue to depart from the Nash equilibrium. And in fact, we plot the movement of the equilibrium in figure B, where there's no noise initially, the equilibria remain on the boundary of the simplex. But as we add a little bit more noise, eventually the equilibrium moves away from the boundary and moves towards the interior of the simplex. And this yields some interesting open questions for the behavior of fictitious play. Number one, what we know that adding noise seems to eventually asymptote out onto a new equilibrium. The immediate question comes up as to what kind of relationship exists between these noisy equilibria and other noisy equilibria that emerge in game theory. For example, the quantal response equilibria or the limit logic equilibrium are all considerations of equilibrium when there's noise added to the system. So is there any relation between the equilibria that we see here and the equilibria that we see in general in game theory? We also wonder whether these results extend to continuous action spaces rather than the discrete action spaces that we've been considering so far. And this question of the reduction of the dynamics when we have complex dynamics, such as limit cycles, when noise is added, we see that there's a simplification of the dynamics towards convergence. Does this generalize towards all games? Now, the experiments seem to show that they do, but it would be an interesting point to explore. Of course, all of these and more are open questions which emerge from our work, and we hope that you find some of them interesting. Thank you for listening.